The Spinosaurus aegyptiacus emerged from the desert of northern Africa like a shadow lost in time, a giant that defies all expectations of what a Cretaceous predator was supposed to be. Its first vertebrae were found in Egypt at the beginning of the 20th century by the expedition of the German paleontologist Ernst Stromer, a man who could not have imagined that this discovery would forever transform the perception of the theropod lineage. Through scattered fragments, such as elongated jaws, neural spines that resembled masts, and disproportionately shaped limb bones, an animal was suggested that deviated radically from the body design known in other large carnivores of its era. But the finding that would mark the fate of Spinosaurus was not only its strange anatomy, but the tragedy that accompanied its legacy. The original fossils, preserved in the Munich Museum, would be destroyed in a bombing during the Second World War, turning the predator into a scientific spectre whose exact form would be reconstructed only from drawings, notes, and new excavations carried out decades later. What was truly astonishing, however, was not only finding the remains of such a singular animal, but discovering incredibly well-preserved anatomical clues that allowed its way of life to be understood. Fragments of recovered jaws showed the perfect alignment of conical teeth, each fitting as if it belonged to an aquatic hunting instrument. In other remains, the internal texture of the bone preserved signs of high density, suggesting adaptation for diving or at least for prolonged immersion. When Moroccan researchers unearthed new caudal vertebrae in scandalously good condition, a tail equipped with bone extensions like a fan was revealed, an improbable structure for a terrestrial predator. It was the tail of a swimmer, not that of a runner. The Spinosaurus was not only a giant, it was an aquatic giant. The best preserved elements allowed the real magnitude of the animal to be understood. It measured more than 15 meters in length, surpassing many of the most feared predators of the Mesozoic. Its dorsal spine, composed of a set of bony projections that could reach 2 meters, was preserved in some specimens with surprising integrity, allowing the form of that emblematic sail that dominated its silhouette to be deduced. Although the function of the structure remains debated, the preserved parts showed muscular insertions and a thickness incompatible with simple ornamentation. Some researchers imagine it acted as a thermal regulator, others attribute functions of display or energy storage. However, what made this predator unique was not the sail itself, but the entire anatomical set preserved in a disturbingly revealing state regarding its amphibious nature. Parts of the skull recovered in an almost intact state showed nasal openings positioned toward the back, a common feature in animals that need to keep their snout in the water while searching for prey. The arrangement of the teeth, perfectly aligned, suggested a predator specialized in large fish, a hunter capable of ambushing from turbid waters. What remained of the palate showed sensory canals similar to those of modern crocodiles, indicators of a system for detecting aquatic vibrations. These details, fossilized with microscopic precision, speak of a way of life that paleontology doubted for decades. A theropod that had abandoned terrestrial supremacy to dominate the rivers, lagoons, and mangroves of ancient northern Africa. One of the most striking findings emerged in Kem, a Moroccan site famous for its abundance of fossils. There appeared vertebrae and parts of the limbs of Spinosaurus with exceptional preservation that allowed almost complete muscular insertions to be observed. The bones of the legs, dense and robust, contrasted with what was expected of a runner. They were not the light and hollow bones typical of large theropods. They were more compact structures, perfect for supporting weight in an aquatic environment and for counteracting buoyancy. The shape of the femur, the proportions of the tibia, and the reduced size of the hind limbs told a story of radical adaptation. The Spinosaurus aegyptiacus had evolved to swim, propelling itself more with its tail than with its legs. The caudal elements recovered with an extraordinary level of preservation offered the definitive proof. Each neural spine of the tail extended laterally, forming a tall, compressed, and flexible structure. This peculiar morphology suggested an undulatory propulsion similar to that used by aquatic animals today to swim efficiently. For the first time in history, a theropod dinosaur showed direct evidence of specialized aquatic locomotion. The exceptional preservation of these remains allowed the creation of models that demonstrated how the tail generated a propulsive force almost comparable to that of modern caimans. The images that emerged from this information brought to life a hybrid predator, half river beast, half hunter of flooded lowlands. The region of the Sahara in which Spinosaurus aegyptiacus lived was not a desert, but a lush mosaic of wide rivers, swampy plains, and deep lakes. The sedimentary layers where the fossils were found preserved not only bones, but remains of giant fish, shark teeth, fossilized scales, and mineralized logs that spoke of a dense and dynamic ecosystem. The preservation of certain bony elements of Spinosaurus amid this set was so precise that it retained slight deformations produced by river currents before final burial. This level of detail allowed the reconstruction of the conditions of the environment that surrounded it in life. This predator may have moved stealthily through dark waters, following shoals and ambushing unsuspecting prey from below. The jaws, recovered in varying degrees of integrity, offered another notable element of preservation, wear marks and microfractures that formed while the animal was still alive. This made it possible to infer its type of prey and the frequency with which it bit slippery catches. The cranial sutures, still distinguishable despite millions of years, offered clues about the strength of its bite, possibly not as powerful as that of other theropods, but perfectly designed to hold enormous fish such as Onchopristis and other aquatic giants that shared its habitat. The Spinosaurus aegyptiacus remained an enigma for decades, a ghost among the pages of paleontology, until the most recent fossils, preserved with an unsettling level of detail, allowed its true nature to be reconstructed. Each bone revealed in the sands of the Sahara contributed a piece of a puzzle that had miraculously survived in different corners of the desert. Some remains still displayed the porous texture typical of fresh bone before fossilization, an exceptionally rare trait. Others preserved signs of internal vascular canals with a clarity rarely seen in dinosaurs of this size. It was as if time had decided to pause for an instant to witness the life of that giant. Today, the modern image of Spinosaurus aegyptiacus is no longer that of a terrestrial predator chasing its prey across dunes and arid plains, but that of an amphibious being sliding its colossal body through muddy waters. Its anatomy, reconstructed thanks to exceptionally preserved finds, shows it as the pinnacle of aquatic adaptation in a lineage of predators designed for solid ground. Each recovered bony element, each dorsal spine, each tooth set perfectly in its alveolus, each extended caudal vertebra, tells the story of an animal that did not fit the traditional molds of the Mesozoic. The Spinosaurus aegyptiacus survived in the fossil record in a fragmented but exceptionally revealing manner, challenging previous theories and forcing the rewriting of what we believed we knew about theropod dinosaurs. Its remains, scattered between Egypt and Morocco, preserved in multiple degrees but always with surprising details, show the complexity of a predator that dominated an aquatic world that disappeared millions of years ago. Dakota the Edmontosaurus annectens from the United States. The discovery of Dakota the Edmontosaurus annectens that revolutionized the image of the Cretaceous world began almost accidentally on the plains of North Dakota, a territory where erosion slowly exposes the secrets buried beneath millions of years of sediment. It was in 1999 when a teenager, Tyler Lyson, found a suspicious protrusion sticking out of the ground. What at first seemed like just another sedimentary rock ended up revealing itself as one of the best preserved dinosaur fossils with soft tissue ever found. Over time, that hardened shape would show not only intact bones but also mummified skin, muscles contracted by dehydration, and anatomical details impossible to imagine in a dinosaur that lived more than 67 million years ago. Unlike most fossils, which preserve mainly mineralized bone structures, Dakota revealed complete traces of the Edmontosaurus's body, as if it had been wrapped in fine sand moments after its death. Its skin, wrinkled like parchment, preserved polygonal scales distributed in specific patterns according to each anatomical region. The neck showed small, almost rounded scales. The torso displayed larger hexagonal scales. The tail, by contrast, preserved elongated scales that seemed to guide the flexion of the body. The level of detail was so extraordinary that in some areas even variations in dermal thickness could be distinguished, indicating that different zones of the body fulfilled distinct physiological functions. The preservation of the skin allowed for an unprecedented anatomical analysis. Researchers could decipher the underlying musculature by observing the undulations and depressions left imprinted in the tissue, a sort of natural mold formed by the contraction of the carcass before completely drying. In the arm region, contours of the triceps muscle and part of the deltoid could be observed, details rarely preserved in dinosaur fossils. In the abdomen, the layers of skin showed folds that suggested the position of the internal organs. The hind limbs preserved, in some areas, impressions of muscle fibers that allowed the reconstruction of the leg strength of Edmontosaurus, an herbivore capable of moving on both 2 and 4 legs, depending on the situation. The discovery of Dakota not only revealed the external form of the animal, but also its physical condition before it died. Later studies indicated that the Edmontosaurus was neither sick nor weakened at the time of its death. On the contrary, it exhibited a healthy body mass, reflected in the uniform thickness of the preserved tissues. This condition raised new questions about the circumstances of its demise. Was it swept away by a sudden flood? Did it become trapped in a muddy area? Or was it the victim of a predator's attack that fatally wounded it? The texture of the skin in certain areas showed marks and grooves that some paleontologists interpreted as possible signs of scavenging, while others supported the hypothesis of rapid burial caused by an abrupt geological event. The exceptional preservation even allowed for the inference of the approximate color of some parts of the body. Although the original pigments are not preserved, the distribution of scales and the presence of microscopic structures related to melanin suggested a coloration ranging between light brown and beige, ideal for camouflage in the forests and plains of the late Cretaceous. Dakota offered a window that no other fossil had ever opened so clearly: what a dinosaur actually looked like in life. Edmontosaurus annectens was one of the most abundant herbivores of its time, a hadrosaur more than 11 meters long and up to 4 tons in weight, equipped with a wide, toothless beak at the front, ideal for stripping large amounts of vegetation. But Dakota revealed a side of this animal never before seen. The fossil allowed direct observation of the arrangement of the tail, whose musculature appeared more developed than previously thought, suggesting that it likely played an important role in locomotion and balance. The skin of the tail, preserved in long segments, showed scales organized in bands that repeated uniformly, offering information about the flexibility of the region and its function during movement. One of the most surprising areas of the discovery was the right arm. The skin covering it had contracted in such a way that it preserved the shape of the muscles, and in some sections, even the outlines of tendons could be distinguished. These details revealed the strength Edmontosaurus needed to support itself on 4 legs while feeding, as well as the ability to use its forelimbs to push branches or stabilize its body on uneven terrain. In the hip region, the preservation of tissue allowed the shape of the gluteal muscles and the structure of the ligament anchoring the tail to the spine to be inferred, essential data for understanding the animal's biomechanics. Dakota's torso, with its hardened yet intact skin, preserved a scale pattern that varied in size according to the curvature of the body. On the flanks, oval scales several millimeters wide could be observed, while in the more exposed areas, such as the shoulders, the scales became more robust and geometric. Paleontologists identified zones where the skin had folded, as if the animal had been lying on its side just before burial. These marks suggested a chronology of decomposition, indicating that the carcass had remained outdoors long enough for the skin to begin drying, but not long enough to deteriorate completely. The fossil even provided information about possible interactions with other organisms. On the surface of the skin, small perforations and grooves were found that could correspond to bites from small scavengers or the movement of necrophagous insects. These tiny marks, preserved with clarity, opened a rare chapter of Cretaceous ecology, the interaction between a dinosaur carcass and the animals involved in the decomposition process. Each groove, each small hole, was a silent trace of an ecosystem that continued its activity even after the death of the giant herbivore. The analysis of the area where the fossil appeared indicated that Dakota died in a floodplain environment, a landscape marked by shifting channels, seasonal flooding, and deposits of fine sand. This type of environment is ideal for the preservation of soft tissues, as rapid burial followed by arid or low oxygen conditions minimizes decomposition. The sedimentary layers surrounding the fossil showed variations in grain texture that allowed the precise moment at which the Edmontosaurus became buried to be reconstructed. This geological precision explained why the skin, muscles, and other structures remained almost intact for millions of years. Another fascinating detail of the fossil was the preservation of the outline of the hand. Although the bones were present in their proper place, the skin around them preserved the shape of the soft tissues surrounding the fingers, allowing scientists to understand what the forelimb of Edmontosaurus actually looked like. Paleontologists could distinguish the form of the pad that contacted the ground, as well as the precise length of the digits and the arrangement of the scales in that area. This level of detail provided the most complete image ever obtained of a hadrosaur in life. Dakota was not simply a fossilized skeleton, it was an entire body trapped in a geological instant. Its exceptional state of preservation offered an anatomical narrative that no artistic reconstruction, no matter how elaborate, had ever been able to capture. The texture of the skin, the muscular marks, the natural folds of the body, the traces of decomposition, and even the post-mortem interactions with other living beings composed a fossilized biography that brought scientists closer than ever to the animal that once roamed the forests and plains of the late Cretaceous. The giant ground sloth with fur, Patagonia, Argentina. In the vast Patagonian immensity, where the wind drags particles of dust that seem to tell ancient stories, one of the most surprising discoveries in South American paleontology took place: the finding of a giant ground sloth whose fur, skin, and tissues were preserved with an almost impossible level of detail. Patagonia, with its extreme climate and arid soils, is a territory that rarely allows the preservation of soft organic matter. However, in a half-buried cave near the central plateau of Santa Cruz, researchers found a body so exceptional that it seemed to have been taken directly from the Pleistocene. There, in the cold and silent dimness, lay the colossal animal, a representative of the mylodontids or megatheriids, relatives of modern sloths but of inconceivable dimensions, still with tufts of hair attached to the skin and with fragments of connective tissue hardened by the passage of time. The discovery occurred at the end of the 19th century, when explorers and scientists began venturing into the Patagonian caves in search of evidence of large extinct mammals. What they found exceeded all expectations. Inside the cave of the Megalodon, as it would later be named, enormous pieces of dry skin appeared, nearly 2 centimeters thick, covered with dense and rough fur that was preserved with a surprising texture. The skin retained, embedded in its surface, small osteoderms, millimetric bony plates that formed a light armor, a natural protection that had endured almost intact for more than 10,000 years. That level of preservation had no precedent. The pieces looked like tanned leather with irregular edges, but clearly recognizable as part of the body of a giant herbivore that had once walked the cold steppes of the region. Along with the hide and fur, the researchers found massive claws, partially mummified tendons, and coprolites, that is, fossilized excrement that still preserved plant remains, offering a direct look into the animal's diet. Long bones, vertebrae, and fragments of the skull were also found, many of them in perfect condition. The combination of these elements made it possible to almost completely reconstruct the giant ground sloth, an animal that could measure more than 3 meters long and easily reach the size of a modern bear, although more robust and with limbs designed for digging, tearing shrubs, and defending itself from the great predators of its time. The most striking aspect of the discovery was not only the physical integrity of the material found, but the evidence that some pieces of skin still retained hardened fat and connective tissues. There were areas where the fur appeared matted, as if the animal had died in a humid environment before slowly drying. Other fragments showed long tufts of hair, brittle but complete, reflecting yellowish-brown tones, probably similar to those it had in life. The preservation of the fur provided crucial information about its adaptation to the cold and the unpredictable climate of the late Pleistocene in Patagonia. Every strand of hair was a silent trace of an ecosystem that had disappeared with the advance of post-glacial warming and the arrival of the first human groups to the region. The cave where these remains were found functioned for centuries as a natural shelter. The dry floor, permanent darkness, and low microbial activity created an ideal microclimate for natural mummification. However, the walls also told their own story. On the rock panels were deep marks left by the animal's own claws, as if it had tried to cling or find a way out. These incisions, perfectly preserved, allowed scientists to imagine the daily life of the giant sloth, a slow but formidable herbivore capable of standing on its hind legs and using its claws as powerful tools to tear vegetation, dig up roots, or defend itself from the fearsome saber-toothed felines that inhabited the region. Among the strangest findings were compact tufts of hair rolled together, known as hairballs, which suggested that the animal probably scratched itself frequently or accumulated shed fur in certain areas of its body before losing it. Analysis of the hair revealed that it had thick, hollow, and rigid fibers, perfectly adapted for heat retention. This detail allowed scientists to imagine the giant sloth as an animal with thick and abundant fur, probably similar to that of a bison, a camel, or even a modern brown bear in terms of thermal insulation. The quality of the material was so high that for years, some scientists discussed the possibility of conducting advanced biochemical studies, since the fibers retained degraded but recognizable organic molecules. In 1897, the explorer Hermann Eberhard revealed the magnitude of the discovery, attracting the attention of scientists from various parts of the world. Among them was the renowned naturalist Federico Reichert, who described in detail the enormous pieces of hide and tufts of fur. The academic world was astonished by the possibility of studying the skin of an extinct mammal directly. The scientific press of the time spoke of an animal freshly arrived from the past, a comparison that, although exaggerated, conveyed the emotional impact of seeing organic material almost intact after so many millennia. The giant ground sloth quickly came to occupy a unique place in South American paleontology, not only because of its size, but because of the exceptional state in which it was preserved. Another revealing element of the discovery was the identification of coprolites with almost intact plant content. In them were found grass fibers, small seeds, and fragments of leaves that indicated a diet based on shrubs and tough vegetation. This reinforced the view of the animal as an herbivore adapted to cold and dry climates, capable of surviving in a landscape dominated by intense winds and poor soils. The skeleton associated with the remains also offered valuable anatomical information. The animal's skull showed powerful jaws and teeth adapted to constant wear. The limb bones presented robust joints, indicating that the sloth could adopt a temporary bipedal posture, perhaps to reach high leaves or to defend itself. Its vertebral column, composed of wide and resistant vertebrae, revealed an imposing musculature, perfect for supporting the weight of the body during slow but steady movements. Each bone found in the cave, protected by the cold and dry environment, showed a level of integrity almost unchanged, as if the erosion of time had respected the original form of the giant. The mummified skin also offered a crucial anatomical detail: the osteoderms. These small bony plates inserted under the skin protected the animal against predators and impacts. They were distributed irregularly, but their presence indicated that the giant sloth had a form of natural armor. Some fragments of skin showed the osteoderms aligned in rows, while others displayed a more dispersed arrangement. Their study allowed a better understanding of the animal's defensive adaptation, a characteristic that only the exceptional preservation of the material made possible to observe. For decades, the cave of the Megalodon generated speculation among explorers and local inhabitants. Many believed at the beginning of the 20th century that the animal might have survived until recent times due to the excellent state of the remains. Some legends spoke of hairy creatures wandering through the Patagonian mountains, stories that fueled the imagination of writers, adventurers, and anthropologists. Although science soon dismissed these theories, the preservation of the skin and fur was so extraordinary that it was easy to understand why these myths arose. The discovery of the giant ground sloth with preserved fur made it possible to reconstruct not only the form of the animal but also aspects of its behavior, its environment, and its daily struggle to survive in an unforgiving landscape. The late Pleistocene Patagonia, dominated by icy winds and scarce vegetation, shaped this robust and resilient creature. Each fragment of skin, each strand of hair, each claw, and each bone stored in the cave offered a silent testimony of a vanished world. The Pliosaur skull. On the rugged coasts of southwest England, where the cliffs slowly crumble under the insistent strike of the sea, One of the most imposing and best-preserved fossil skulls of all time came to light, that of a gigantic pliosaur, a Jurassic marine predator whose jaws could split almost any creature that dared cross its path in half. The region, known as the Jurassic Coast, is a natural fossil sanctuary where geology exposes strata that sink more than 150 million years into the past. But even in such a prolific place, no one expected to find something so monumental. A skull more than 2 meters long, intact in its proportions and preserved with a clarity that allowed even the internal channels where blood vessels and nerves once circulated to be distinguished. The discovery was made by a group of paleontologists and fossil rescue specialists exploring a section of the cliff at risk of collapse. There, embedded in the rock as if trapped during a moment of marine violence, the outline of the gigantic animal appeared. The first observations revealed enormous, conical, perfectly aligned teeth, many of them still firmly anchored in their sockets. The size and arrangement of the dentition confirmed that it belonged to a pliosaur, a member of a lineage of fierce marine reptiles that dominated the Jurassic oceans with an efficiency comparable to that of today's great white sharks. The preservation of the skull allowed the perfect curvature of the jaws to be appreciated, especially the robustness of the maxilla and the functional elegance of the premaxilla, a structure that in life would have withstood the brutal tension of hunting. The teeth, mostly intact, showed longitudinal striations that acted as reinforcement to prevent fractures when biting prey with hard shells or resistant bones. Some dental pieces even preserved the root, making it possible to study how these natural weapons were anchored in the animal's jaw. The external surface of the skull showed different textures depending on the region. Rough areas for muscle insertion, smoother surfaces around the eye sockets, and marked bony crests that speak of the power of the jaws. The pliosaur to which this skull belonged must have measured between 10 and 12 meters long, with powerful flippers that propelled it through the water at impressive speeds. However, what made the find special was not only the magnitude of the animal but the level of microscopic preservation. Internal parts of the bone preserved natural windows, openings that allowed the anatomy to be seen without the need to fracture the piece. Paleontologists observed the channels that housed the trigeminal and optic nerves, the sinus chambers that lightened the weight of the skull, and the delicate septa that separated the respiratory ducts from the oral cavities. Rarely did such an ancient animal preserve with such clarity structures that generally disappear completely during fossilization. The sedimentary environment also played a fundamental role. The skull was surrounded by shales and fine limestones, sediments deposited in a relatively calm marine environment. This allowed the animal's head to be buried quickly, preventing its dispersal by scavengers or currents. But the most surprising aspect was that the fossil did not appear crushed. Most fossil skulls of marine reptiles appear deformed by the pressure of millions of years of sediments. However, this one was preserved three-dimensionally, allowing the real shape of the predator to be studied without having to reconstruct it digitally. The pliosaur's eyes, located in large orbits, must have provided penetrating vision capable of detecting subtle movements in deep or murky waters. The skull preserved, in the posterior region, a series of crests that reflected the enormous musculature of the neck, allowing the animal to move its head with lethal precision during an ambush. On the sides of the snout, the fossilized nares revealed the exact location of the respiratory openings, oriented so that the pliosaur could take air quickly without exposing too much of its body at the surface. The elongated and narrow shape of the snout, preserved almost without deformation, suggested a predator specialized in grabbing large and slippery prey, such as young ichthyosaurs or short-necked plesiosaurs. The position of the teeth allowed a crucial characteristic to be observed: the perfect interlocking of the jaws. When the pliosaur closed its mouth, the upper and lower teeth fit together like the teeth of a steel trap. This design, visible in the fossil thanks to its impeccable preservation, ensured that no prey escaped once captured. Some marks on the enamel even suggested a wear pattern produced by repeated friction between the teeth when closing the jaws with enormous force. The bite of this animal must have been one of the most powerful of the Jurassic. The interior of the skull also offered valuable information. At the base, paleontologists identified the region where the vertebral column was inserted and the muscular connections that supported the head. The shape of this area allowed inference of the posture the pliosaur adopted in the water, a firm and stable alignment ideal for swimming at high speed without losing hydrodynamic efficiency. The preservation of the nasal structures, in turn, made it possible to deduce how it managed air exchange. It was a lung breather, but its skeletal design suggested a capacity for prolonged immersion. The find also included jaw fragments associated with the skull, allowing the total opening of the animal's mouth to be reconstructed. This could reach impressive angles, sufficient to swallow large prey in a single bite. The sensory tubes on the surface of the snout, fossilized with clarity, indicated the possible presence of receptors that detected movements in the water similar to the sensory system of modern crocodiles. The preservation was so detailed that even small roughness intended for the anchoring of soft tissues could be observed without any doubt. The discovery caused a commotion in the international paleontological community. The magnitude of the skull, its level of preservation, and the clarity with which it exposed the predator's anatomy made it a unique piece. It was not just an impressive fossil, it was an anatomical time capsule that showed without distortion one of the great hunters of the Jurassic. The flippers, although not present, could be easily imagined based on the cranial musculature and the movement patterns suggested by the skull. The extraction of the fossil was a race against time. The specialists had to rescue it before the cliff collapsed and the skull was lost forever in the sea. The process required the placement of harnesses, scaffolding, and protective nets while waves struck relentlessly at the base of the cliff. Each blow of the sea reminded them that geological time, although vast, is also vulnerable to immediate destruction. After weeks of work, the skull was secured, wrapped in a protective casing, and carefully transported to the laboratory where it finally revealed all its secrets. Once in the hands of the experts, the skull showed details that had gone unnoticed during the excavation. On the bony crests of the upper part, tiny impressions were observed, possibly associated with blood vessels or supporting tissues. The oral cavity preserved the exact shape of the palate, and some areas of the bone showed undulating textures that could indicate the insertion of cartilage or membranes. Every centimeter of the fossil was a silent testimony of an animal that inhabited a primitive, dark, and life-filled ocean. This discovery consolidated the reputation of the Jurassic Coast as one of the most important regions in the world for the study of marine reptiles. The pliosaur skull became an emblem of how nature, under exceptional circumstances, can preserve the vestiges of creatures that dominated ecosystems now vanished. Even without the rest of the skeleton, the head was enough to understand the power, speed, and lethality of the predator. The Lystrosaurus. In the vast fossil record of the planet, few animals represent the resilience of life after disaster like Lystrosaurus. This compact, robust, and singular creature dominated the Earth just after the greatest biological catastrophe known, the Permian-Triassic mass extinction, which occurred approximately 252 million years ago. It survived when 90% of the planet's species disappeared, and it did so by adapting almost instinctively to a transformed world, arid, scorching, and filled with evolutionary uncertainties. However, what would make this animal unforgettable was not only its extraordinary survival story, but also the appearance of exceptionally well-preserved fossils in regions ranging from South Africa to Antarctica, revealing anatomical features with a surprising level of detail for such an ancient animal. Lystrosaurus was neither a reptile nor a mammal, but a synapsid, part of an ancestral lineage from which modern mammals would eventually emerge. It measured between 0.5 meter and 1 meter in length, with a thick body and short legs, ideal for digging and moving through a devastated landscape. Its unmistakable skull was almost triangular, with a short snout and a powerful jaw adapted to tearing up roots and tough vegetation. But beyond its compact appearance, the exceptionally preserved fossils allow us to observe details rarely found in other Triassic beings. Impressions of skin, delicate molds of cartilage, internal cavities reflecting its physiology, and even traces of how it breathed on a newly rebuilt planet. One of the most notable discoveries came from the Karoo Basin in South Africa, where river sediments captured Lystrosaurus bodies in an unusually three-dimensional state of preservation. In some cases, the ribs remained impeccably articulated without crushing, which made it possible to reconstruct the shape of the thorax with complete precision. This led to a fundamental finding. Lystrosaurus possessed a primitive diaphragm and probably breathed more efficiently than many of its contemporaries. Its ribcage, preserved without distortion, showed a pattern of muscle insertion indicating a respiratory system more similar to that of mammals than to that of modern reptiles. In a world with dangerously low oxygen levels, this advantage may have made the difference between survival and extinction. The texture of the bone surface in some exceptionally preserved skulls made it possible to observe areas where nasal cartilage was attached. This detail suggested that Lystrosaurus had a flexible snout, perhaps with a structure similar to that of modern pigs, ideal for exploring the ground in search of tubers or underground sprouts. Some sedimentary molds even preserved the external shape of the upper lip, an absolute rarity in such ancient fossils. These impressions revealed a surprisingly expressive creature, capable of moving its snout with great agility to manipulate vegetation. In other regions of the world, such as Antarctica, which at that time was a forested continent with marked seasons, complete skeletons of Lystrosaurus were found in excellent condition, many of them articulated and showing no signs of being transported by currents. This level of preservation made it possible to reconstruct behavioral scenes. In some sedimentary layers, several individuals appeared together, suggesting that these animals may have lived in small groups or at least sought the same refuges during adverse climatic conditions. Their bodies, found in flexed and protected positions, hinted that Lystrosaurus may have dug temporary burrows or sought natural cavities to shelter from extreme heat or sudden storms. The dentition of Lystrosaurus, preserved with extraordinary precision in many fossils, was one of its most distinctive features. It had only two large tusks, which projected forward like two curved chisels. The rest of the jaw was toothless, implying a feeding system based on cutting and pulling vegetation before grinding it with powerful jaw movements. The internal surface of the skull, preserved in some specimens, showed the nerve channels responsible for jaw musculature. This made it possible to calculate the force with which it could bite, a surprisingly high value for an animal of its size. One of the most astonishing findings related to the exceptional preservation of Lystrosaurus occurred in Russia, where volcanic sediments sealed entire bodies almost instantly. These fossils, closer to mineralized mummies than to simple bones, even preserved traces of skin tissue. In certain impressions, it was possible to distinguish relatively smooth skin with no visible scales, supporting the theory that early synapsids had dermal textures more similar to those of mammals than to those of reptiles. The absence of scales would also align with the need to regulate body temperature in a world recovering after the environmental collapse of the Permian. Other specimens presented evidence of accelerated growth, with visible growth lines in the bone thanks to the exquisite preservation of the internal microstructure. This suggested that Lystrosaurus had a higher metabolic rate than most animals of the early Triassic. It grew rapidly, reaching adulthood in a short time, an evolutionary strategy key to repopulating a devastated planet where predators were still scarce but environmental conditions changed relentlessly. The idea that this creature could have become the dominant terrestrial vertebrate of the world for several million years seemed improbable, but the preserved fossils confirmed it clearly. One of the most intriguing aspects of its exceptional preservation was the frequency with which individuals were found in typical resting positions or in postures indicative of death by lack of oxygen. Geologists deduced that many died during extreme climatic events or prolonged droughts, becoming trapped in mud zones hardened by heat. When rains returned suddenly, the bodies were buried in thin layers of sediment before decomposing. This combination of rapid death, swift burial, and arid environment was essential for the skeletons to reach us in such complete condition. The fossils of Lystrosaurus also reveal clues about the landscape they inhabited. In the sediments surrounding the bodies, remains of pioneer ferns and carbonized trunks were found, signs of a world that experienced frequent fires followed by surprisingly rapid plant regeneration. This cycle of destruction and renewal formed the backdrop of the early Triassic, and Lystrosaurus, with its resilient physiology and opportunistic behavior, became one of the clearest symbols of the tenacity of life. Another striking detail in the preservation of some specimens was the intact condition of the auditory canals. Although the inner ear was lost during fossilization, the cavities displayed a relatively advanced design, raising the possibility that Lystrosaurus had a more developed sense of hearing than previously believed. This would have been crucial in an open environment where the first early Triassic predators were beginning to proliferate. The presence of juvenile bones near well-preserved adult skeletons raised questions about parental behavior. Although no direct evidence of parental care has been found, the high preservation of the fossils allowed researchers to detect concentrations of individuals of different ages in the same layer. This could indicate that certain groups of Lystrosaurus moved together or that environmental conditions led them to gather in the same refuges during difficult periods. Lystrosaurus, thanks to these exceptional discoveries, ceased to be just a name in paleontology books. It became a tangible, almost familiar creature whose skin, bones, skull, and fossilized posture allowed its life to be reconstructed with surprising closeness. The way these fossils managed to withstand the passage of millions of years is a reminder that even in the darkest periods of Earth's history, life finds ways to leave clear traces of its presence. The Yutyrannus, China. In the vast geological formations of northeastern China, where nature has preserved one of the most detailed fossil records on the planet, a discovery emerged that profoundly altered the perception of large theropods, Yutyrannus huali. This early Cretaceous predator possessed the majesty of its tyrannosauroid relatives, but with an unexpected characteristic that challenged every previous reconstruction. It was covered in feathers. The extraordinary preservation of its fossils, especially the clear and visible presence of feather-like filaments around the body, made Yutyrannus one of the most impressive examples of soft tissue preservation in large carnivorous dinosaurs. The discovery took place in the Yixian Formation, a region famous for its exquisitely preserved fossils in extremely fine volcanic shales. It was there that paleontologists identified 3 nearly complete skeletons of Yutyrannus, 1 adult and 2 juveniles, each showing with remarkable clarity dark patches and filamentous patterns adhered to the rocks. These filaments represented structures similar to proto-feather filaments, a primitive form of plumage that covered much of the animal's body. The sharpness with which they were preserved allowed scientists to observe the length, distribution, and density of these feathers, revealing unprecedented detail in a dinosaur nearly 9 meters long and weighing more than 1.5 tons. The presence of feathers in Yutyrannus was not only surprising because of its size, but also because of the extraordinary clarity of the preservation. In many areas around the ribs, hips, and the base of the neck, the feather filaments were arranged in fans or tufts, as if they had remained attached to the body even after death. The dark texture of the filaments contrasted with the lighter sedimentary matrix, making it possible to distinguish their shape and length, some exceeding 10 centimeters, an exceptional record for a large theropod. Paleontologists observed that the plumage was not distributed uniformly, but instead formed especially dense concentrations on the torso and hind limbs. This suggested an insulating function in a climate colder than traditionally thought for the Cretaceous. The Yixian Formation, at the time of Yutyrannus, was a seasonal environment with cold winters and frequent snowfall. The presence of this plumage, preserved in spectacular fashion, indicated that the predator had evolved to tolerate low temperatures, something unthinkable for a theropod of such size before the discovery. The skull of Yutyrannus, also exceptionally well preserved, showed key anatomical details for understanding its behavior as a predator. The jaw was robust, with long backward curved teeth designed to tear flesh. The eye sockets, large and well-defined, suggested considerable visual acuity, likely useful for detecting prey at a distance. The nostrils, positioned high, indicated a notable sense of smell. However, the most impressive elements were the skin and feather impressions around the face. Some regions appeared to show areas without feathers, which might have meant that this portion of the skull was covered only by scaly skin, as seen in many modern scavenging birds. The skeleton of Yutyrannus revealed powerful proportions. Its hind legs, drastically longer than the forelimbs, were adapted for fast and efficient movement. The hip, exceptionally well preserved in one of the specimens, clearly showed the structure of muscle insertions, providing clues about its acceleration capabilities. Although not as agile as smaller theropods, Yutyrannus could generate quick bursts of speed over short distances, likely enough to ambush weakened prey or the young of other large herbivores in the region. The degree of preservation allowed scientists to analyze even internal features. In some neck and back bones, marks of ossified tendons could be seen, structures that persist through fossilization and help reconstruct the animal's muscular system. These characteristics, combined with the presence of feathers, painted a clear picture of Yutyrannus as a muscular predator covered in a down-like mantle. This duality, which blended the ferocity of a tyrannosaur with the feathered appearance of an animal adapted to cold, made the fossil one of the most striking of the past decades. The geological formation where Yutyrannus was found was an active volcanic region during the early Cretaceous. Frequent eruptions produced clouds of fine ash that settled quickly over the local fauna, capturing anatomical details with almost photographic fidelity. In the case of Yutyrannus, this ash preserved not only the skeleton, but the outline of the body and the feathers, turning its death into a time capsule that survived more than 124 million years. The juvenile remains found alongside the adult showed similar characteristics in plumage and bone structure. However, what sparked discussion among paleontologists was whether the group represented a social unit or simply individuals that died in the same volcanic event. The preservation of feather filaments in the juveniles was even sharper, allowing the observation of differences in plumage density that may have been related to age. Young individuals possessed denser concentrations of short feathers along the neck and back, indicating that thermal insulation was essential from early stages of life. The preservation of Yutyrannus also offered a unique opportunity to study the evolution of plumage in non-avian dinosaurs. While many smaller species had shown evidence of feathers or proto-feathers, never before had such a large theropod displayed this level of preservation. This detail prompted a reconsideration of the relationship between body size and the presence of plumage, challenging the idea that only smaller dinosaurs retained these features for thermal reasons. Another surprising element was the preservation of skin impressions in areas without feathers. On parts of the tail, for example, the rocks displayed patterns of fine scales, similar to those of some non-feathered theropods. This coexistence of feathers and scales revealed that Yutyrannus represented an intermediate evolutionary stage in which plumage coexisted with regions of hardened skin, possibly to facilitate movement or protect certain parts of the body. The exquisite preservation also made it possible to observe the structure of its hands and claws. The fingers, long and armed with curved claws, had left impressions in the sedimentary matrix, even preserving partial imprints of soft tissues surrounding the bases of the phalanges. This indicated that the hands of Yutyrannus had a level of tactile sensitivity unexpected for a predator of its size, possibly useful for manipulating prey or interacting with the environment before the final ambush. Yutyrannus became, thanks to this extraordinary preservation, one of the most iconic dinosaurs in the Chinese fossil record. Its image as a feathered colossus walking among volcanic forests transformed public perception of large theropods and forced a reimagining of the appearance of many of its close relatives. The presence of feathers, preserved with such detailed clarity, was a revelation for modern paleontology, which for decades had envisioned tyrannosauroids as scaly-skinned creatures with no trace of plumage. The Allosaurus jimmadseni, Big Joe. In the reddish deserts of Utah, where the wind slowly carves the rock walls and exposes fragments of the past with almost surgical delicacy, one of the best preserved predators of the late Jurassic appeared, the Allosaurus jimmadseni, known as Big Joe. This specimen, found in an extraordinary state of preservation, opened an exceptional window into the true anatomy of one of the great hunters of its time. Before Big Joe, Allosaurus was already one of the most studied dinosaurs in North America. However, the appearance of this articulated and nearly complete specimen allowed researchers to observe details that rarely survive the fossilization process and transformed the understanding of how this emblematic predator lived and hunted. The discovery took place in the Morrison Formation, a region famous for its wealth of dinosaur fossils. There, buried in layers of hardened sand, the bones of Big Joe were found in positions suggesting that the animal died in a relatively calm environment, perhaps beside a watercourse that later covered it with fine sediments. When paleontologists began the excavation, they soon realized they were not facing a common Allosaurus. The vertebral column remained almost completely articulated, the ribs followed a natural arc, and the skull, usually one of the first elements to fragment, was preserved in such immaculate condition that each muscle insertion groove could be studied with a level of detail worthy of much more recent specimens. One of the most impressive aspects of Big Joe was the preservation of the skull. It showed all the sutures without major deformations, which made it possible to understand how the bony plates of the Allosaurus were assembled in life. The cranial openings, called fenestrae, appeared intact, revealing a light but strong system, perfect for a predator that depended as much on the mobility of its head as on the strength of its jaws. The teeth, long and serrated, remained firmly set in the jaws, and several still retained a sharp edge as if they were ready to tear fresh flesh. The three-dimensional preservation of the skull allowed researchers to study its biting mechanism, revealing that Allosaurus did not attack with the vertical crushing force of other theropods, but with a hatchet-like slicing motion, using the neck muscles to generate impact and tearing. The forelimbs of Allosaurus were one of its most feared tools, and in Big Joe they were found in an exceptional state of preservation. Each phalanx and each claw remained fully articulated. The claws, curved and sharp, even preserved the surface texture, with grooves meant to hold keratin sheaths in life. The proportions of the limbs showed that Allosaurus used its arms not only to hold prey, but also to lift itself and stabilize the body during attacks. The excellent preservation of the arm bones allowed for an accurate reconstruction of the strength and mobility of the joints, revealing a much more dynamic range of motion than previously estimated. Big Joe's torso provided a surprising view of the biomechanics of Allosaurus. The ribs, exceptionally preserved, allowed researchers to observe their natural arrangement, forming a narrow but deeply arched thorax ideal for housing long and efficient lungs. Some rib bones even showed ligament marks, fossilized impressions where soft tissues once attached to the bone, which is considered a rarity in dinosaur fossils. Because the thoracic cavity was practically intact, it was possible to infer the size and position of the animal's main organs, as well as its respiratory capacity and efficiency during prolonged hunting activities. Big Joe's vertebral column, from the neck to the tail, was almost entirely articulated. This continuous series of bones made it possible to observe the natural curvature of the body and the shape of the spinous and transverse processes, the bony projections that housed tendons and muscles, without distortion. In particular, the cervical vertebrae showed an elegant structural design that demonstrated a powerful and flexible musculature capable of quick and precise movements during hunting. Meanwhile, the tail vertebrae showed how the tail acted as a counterbalance during locomotion, allowing Allosaurus to maintain balance while running or making abrupt turns to chase prey. The hind limbs were another pillar supporting the predatory image of Allosaurus, and in Big Joe they were preserved with extraordinary detail. The femur, tibia, and fibula were complete, showing the articular surfaces without fractures. The proportions of the bones revealed an animal built for speed and thrust, capable of reaching significant speeds over short distances. The foot, articulated with its claws, preserved the exact shape of the phalanges, which helped researchers understand how Allosaurus distributed its weight and how it manipulated the terrain with each stride. One of the foot bones even preserved subtle marks associated with natural wear, indicating that Big Joe had walked long distances before dying. The skin, although not directly preserved, left partial impressions in the rock around some ribs and in fragments of the pelvis. These impressions showed a texture of small, rounded scales similar to those found in other theropods, arranged in irregular but consistent patterns. The clarity of these impressions was sufficient to reconstruct the external appearance of certain regions of the body, making them a valuable piece of evidence for interpreting the skin surface of Allosaurus. Paleontologists also found evidence of pathologies in Big Joe's skeleton, preserved clearly due to the fossil's exceptional quality. One of the ribs showed signs of a healed trauma, probably the result of a blow or bite that occurred long before its death. The fracture had partially healed, indicating that the dinosaur survived at least weeks or months after the incident. This detail revealed a more intimate aspect of the animal's life. Big Joe had endured injuries in combat and yet continued hunting and moving through its territory. The environment in which Big Joe was found also helped explain its degree of preservation. The Morrison Formation was a landscape dominated by meandering rivers, floodplains, and areas of rapid sedimentation. It is possible that the Allosaurus died near a riverbank and that a sudden flood quickly buried it, preventing the body from being scattered by scavengers or currents. This rapid burial, combined with the region's relatively dry climate, favored the three-dimensional preservation of the skeleton. The discovery of Big Joe represented a scientific milestone. It was not only one of the most complete Allosaurus specimens ever found, but also one of the best preserved, allowing researchers to study the predator's anatomy with a level of meticulousness rarely achieved. With this fossil, paleontologists were able to create more precise muscular models, more realistic biomechanical reconstructions, and more accurate comparisons with other theropods. Big Joe became a key figure in understanding how the great predators of the late Jurassic lived. Its skeleton, articulated and surprisingly intact, demonstrated the lethal elegance of an animal that roamed the open meadows and forests of North America more than 150 million years ago. Its exceptional preservation was a direct invitation to reconnect with a past that is rarely preserved with such fidelity. Sarcosuchus imperator, the super crocodile of the Sahara, Niger. In the scorched deserts of central Sahara, where dunes hide ancient river plains and dry valleys hold the memory of lost worlds, one of the most striking discoveries in modern paleontology emerged: Sarcosuchus imperator. This colossus of the early Cretaceous, justly nicknamed the super crocodile, dominated the rivers and lakes of the ancient Sahara more than 110 million years ago. Its gigantic body, capable of reaching 12 meters in length, seemed taken from a realm of prehistoric nightmares, and the exceptionally well-preserved remains found in Niger allowed its anatomy to be reconstructed with an accuracy that few fossil reptiles have ever achieved. The most significant discovery was made in the region of Gadufawa, a fossil oasis in the heart of the Tenere Desert. There, among sun-scorched reddish rocks, researchers found a colossal, nearly complete skull measuring about 2 meters long. When the fossil prey was carefully removed from the sandy matrix, it displayed details that rarely survive through time: the rough surface of the snout, the rows of long, conical teeth, and the cranial sutures outlining each bony plate with surprising clarity. It was almost impossible not to imagine that monster silently prowling from murky waters, waiting for the right moment to lunge at a thirsty dinosaur that ventured too close to the shore. The snout of Sarcosuchus, carefully preserved, had an elongated and robust shape, resembling a disproportionate mix between a modern crocodile and a gharial. But the most striking feature was the bony bulge at the tip of the snout, a bulbous structure known as the bulla, observed for the first time in this exceptionally preserved fossil. Although its function remains uncertain, some paleontologists suggest it may have served to amplify low-frequency sounds used in displays or territorial signals. What was extraordinary was that the surface of this structure was almost intact, allowing its shape to be analyzed without speculative reconstructions. The skull displayed numerous natural openings that lightened its weight, yet it remained a crushing weapon. The jaws, preserved in an almost anatomical position, showed endless rows of pointed teeth, each one fitting perfectly with its counterpart. Several teeth even retained the original enamel striations, a feature that helped determine how Sarcosuchus gripped its slippery prey. Some teeth were fractured in ancient times, and the bases of those fractures showed patterns of bone remodeling, clear signs that the animal survived long after those injuries, a testament to a life filled with violent confrontations. Another impressive aspect of the discovery was the partial preservation of the dorsal armor. Unlike modern crocodiles, whose bony plates usually preserve separately, several osteoderms of Sarcosuchus were found still in anatomical arrangement, forming a series of protective shields aligned along the back. These osteoderms were enormous, some as large as plates, and displayed a rough texture adapted to resisting blows and bites. Their size and distribution suggested that the animal was capable of withstanding the attack of large predators, or even confronting members of its own species in deadly territorial conflicts. The vertebrae of the body and tail were also found in a remarkable state of preservation. The vertebral structure, robust and articulated into long segments, indicated that Sarcosuchus possessed extremely powerful musculature, useful for diving rapidly or launching attacks from semi-aquatic positions. Some vertebrae showed muscular insertions so well defined that the attachment points of major tendons were still visible. These features revealed a predator specialized both in explosive ambushes and in dragging large prey into the water, much like modern crocodiles do. The sedimentary environment of the region reinforced the story of the supercrocodile. The remains were found in ancient fluvial layers formed by extensive rivers and meanders that flowed through a Sahara completely different from today, a landscape of open woodlands, lakes, and abundant aquatic fauna. The presence of bones from giant fish, enormous turtles, and herbivorous dinosaurs confirmed that Sarcosuchus shared its domain with a multitude of potential prey. The exceptional preservation of the bone material even allowed bite marks to be observed on other fossils from the region, attributable to Sarcosuchus due to their unique serration pattern. The preserved maxilla offered an unsettling clue: the bite force. The bony projections in the rear region of the skull displayed broad surfaces for the insertion of extremely strong musculature. Although the exact force cannot be measured without living animals, comparisons with modern crocodiles suggest that Sarcosuchus may have possessed a brutal bite capable of splitting large bones or piercing the shells of giant turtles. Observing the skull, one could imagine the unimaginable pressure it exerted in the final instant of an ambush. In some fragments of the rib cage, partial impressions of soft tissues were identified, preserved as thin mineralized layers showing the natural curvature of the torso. The presence of these impressions indicated that the animal had been buried rapidly, likely after a sudden collapse of fluvial sediments or an abrupt river flood. These events, capable of burying large animals within minutes, were common in the early Cretaceous Sahara, where seasonal rains generated unexpected inundations. The specimen from Niger also preserved parts of the forelimbs and hind limbs with surprisingly intact joints. The bones of the arms, short and powerful, indicated that Sarcosuchus was capable of moving on land more effectively than modern crocodiles are typically thought to do. The hind limbs, longer and more robust, reinforced this idea, suggesting that the supercrocodile could cover short distances on land with surprising speed, especially during migrations between bodies of water or in brief pursuits. Despite its colossal size, Sarcosuchus imperator was not a solitary hunter in a desert environment. It shared its territory with herbivorous dinosaurs, giant fish such as Morsonia, enormous turtles, and other large predators. The preservation of various remains related to this animal allowed researchers to infer its ecological role. It was an apex predator capable of confronting almost any creature in its ecosystem. The clarity with which its skull, osteoderms, vertebrae, and limbs were preserved offered a clear image of an imposing hunter, elegant in its violence and adapted to an aquatic world full of opportunity. Sarcosuchus imperator, captured in stone as if death had surprised it in mid-ambush, represented an extraordinary testament to the African Cretaceous. Each bone, each tooth, and each bony plate preserved in such detail narrated the life of a predator that ruled rivers and lagoons with absolute authority. Its size, preservation, and uniqueness made it one of the most impressive giants ever extracted from the Sahara Desert. Megalodon spine, Peru and Panama. In the depths of the geological history of the American Pacific, where marine sediments guard the secrets of creatures that dominated the oceans with incomparable ferocity, one of the most unexpected discoveries related to the largest shark that ever existed appeared: Otodus megalodon. Unlike most fossils of this colossal predator composed almost exclusively of scattered teeth, certain sites in Peru and Panama revealed a form of exceptional preservation that rarely appears in the fossil record: articulated vertebrae, complete and arranged as if the spine had remained suspended in time. This type of preservation, extremely rare in sharks due to the fragility of cartilage, offered an unprecedented view of the internal structure of the marine giant. The most famous discovery occurred in the Sarcosuchus region on the southern coast of Peru, a place where ancient ocean floors were exposed after millions of years of tectonic uplift and coastal erosion. There, a sequence of colossal vertebrae, some the size of plates and others reaching even larger dimensions, appeared aligned almost in their original position, forming a column that revealed with extraordinary precision the shape and proportion of the back of an adult megalodon. Their diameter, thickness, and internal texture allowed scientists to calculate the animal's age, muscular strength, and in part, its swimming capacity. The vertebrae preserved in Peru showed a level of detail that exceeded what is usual in fossilized cartilage. Each one displayed clearly marked growth rings, something similar to concentric laminations resembling tree rings, which allowed researchers to infer that the individual had surpassed 40 years of age. The thicker rings suggested periods of accelerated growth, likely during youth, when the Megalodon experienced a disproportionate increase in size. In contrast, the narrower rings indicated slower growth periods, perhaps associated with variations in food availability or environmental changes. The most striking aspect of the preservation was the clarity of the articular surfaces. The areas where each vertebra connected to the next were so well defined that paleontologists could reconstruct the natural curvature of the spine with precision. This information allowed them to infer the animal's flexibility, the strength of its lateral movements, and the power of the muscles that propelled it through the ocean. In life, the Megalodon would have swum with an undulating style, moving its body through a combination of caudal force and gentle torsions. The preservation of these vertebrae allowed this internal architecture to be seen with almost anatomical clarity. Some of the fossil vertebrae contained mineral inclusions that precisely replicated the internal texture of the cartilaginous tissue. In cross-sections, small radial structures and fossilized vascular channels could be seen, evidence of how nutrients flowed inside the shark's spine. This type of preservation, extremely rare, was only possible thanks to the exceptional conditions of the seabed where the animal died. An anoxic environment, free of scavengers, where the currents were weak enough not to disperse the body remains. In addition to Peru, another extraordinary discovery took place in Panama, where paleontological excavations in marine sediments revealed another series of even more complete Megalodon vertebrae. In this case, the pieces were associated with several teeth, allowing scientists to confirm without a doubt their belonging to the great predator. What was remarkable was that a part of the spine appeared naturally curved, as if the animal had been making a turn or a quick movement when it died. This three-dimensional arrangement, preserved with such fidelity, offered a dynamic image of the shark's body, frozen mid-motion. The Panamanian vertebrae also displayed exceptional marks, small circular erosions and scars that could correspond to pathologies suffered during life. Some appeared to be the result of infections, while others showed signs of regenerative processes, revealing that the Megalodon was not only a formidable predator, but also an animal that faced diseases and survived them for decades. The degree of preservation was such that in certain sections, mineral deposits replicated connective tissues, such as the epicentral cartilages that reinforced the structure of the vertebrae. Each vertebrae found in Panama was colossal in size, with some specimens reaching diameters greater than 20 centimeters. Considering the proportion between the size of the vertebra and the total body length, it was estimated that the individual to whom they belonged had reached more than 15 meters in length. However, some paleontologists suggest that based on the thickness and density of the vertebrae, this specimen might have surpassed even that figure, approaching the upper size limits proposed for Megalodon. The robustness of the spine indicated that the shark could support monumental musculature necessary to propel such a large body at high speeds. The exceptional preservation of the vertebrae also allowed scientists to deduce the real shape of the Megalodon's tail. The last elements of the spine showed a natural upward inclination, which coincided with the pattern of modern lamniform sharks, such as the great white shark. This anatomical clue suggested that the Megalodon possessed a crescent-shaped caudal fin designed for speed, not just power. This detail, visible only thanks to the clarity of fossilization, solidified the image of the Megalodon as a fast swimmer, capable of catching agile prey such as young whales, primitive dolphins, and robust pinnipeds. In Peru, some vertebrae appeared alongside remains of bony fish and fragments of early whales. Although it cannot be confirmed that they were part of the same event, the association suggested an ecosystem rich in large prey, ideal for a superpredator. Cut marks found on nearby cetacean bones, marks that matched the curved shape of Megalodon teeth, revealed the active presence of the shark in the region. The simultaneous preservation of vertebrae and accompanying fauna provided a snapshot of the Miocene ocean, where the Megalodon reigned unchallenged. The exceptional nature of these discoveries also lay in their rarity. Cartilage, being soft and rich in water, rarely fossilizes. In most cases, it disintegrates shortly after the animal's death. However, the conditions of the seabed in certain areas of the South American Pacific created anaerobic environments that favored the rapid and complete preservation of internal structures. These fossilized vertebrae were not only scientifically valuable, they were direct fragments of a body that, under normal conditions, should have been lost forever. In Panama, the three-dimensional preservation made it possible to study the original orientation of the spine. The smooth alignment between vertebrae suggested that the corpse was not significantly disturbed before being buried. This implied that the Megalodon may have died in deep waters, perhaps of old age, disease, or a catastrophic event related to temperature changes or ocean currents. Upon sinking, the body would have reached a calm seabed where the lack of oxygen prevented the usual decomposition. The simultaneous presence of teeth associated with the vertebrae offered another remarkable rarity: the opportunity to study the real size of the jaw in proportion to the spine. The Panamanian teeth were immense, some more than 14 centimeters long, consistent with the size inferred from the spine. These dental pieces even preserved their original enamel and microscopic wear marks produced by contact with the bones of large prey. Each tooth was a silent testament to the colossal force that the predator's jaw could exert. The combination of articulated vertebrae and associated teeth allowed for more complete anatomical reconstructions of the Megalodon than ever before. The precise measurements of the vertebrae showed the natural curvature of the body, while the teeth revealed the animal's enormous predatory capacity. The harmony between these fossilized pieces suggested a robust, muscular, and aerodynamic body, a perfect design to dominate the oceans for more than 20 million years. The discoveries from Peru and Panama offered, with a clarity rare in shark paleontology, a direct approach to the true body of the Megalodon. Its vertebrae, preserved in an exceptional manner, functioned like the cogwheels of a monumental biological mechanism capable of propelling the largest marine predator in history.